axis. Utilizing the parallelogram law, all we need to do is translate our force F1 downwards to the head of our force F2. Similarly, F2 needs to be translated to the head of S1. This creates a parallelogram. Now the diagonal of this will give us our resultant force. Once we have that, we have to identify the internal angles of the parallelogram here as well. Since the angle between axis V and U is 75, this gives us the angle from force F1 to the axis U as 45 degrees. Combining it with the 30 degrees give us one of the internal angles of the parallelogram as 75. Now, by property of the parallelogram, opposite angles are equals to one another. Also, the sum of internal angles of a parallelogram is 360. Based on that, we can identify the other two angles, that is coming as 105 degrees. Now, once we have identified all the internal angles of the parallelogram, we can go ahead and pick one of the triangles and solve for the resultant force utilizing our law of sine and law of cosine. So in this case, since we know the two forces of 4 kilonewton and 6 kilonewtons and the angle between them is 105, we can go ahead and apply our cosine law to solve for the resultant force. That is, square root of our first force is square plus the second force is square minus 2 times the two forces and the cosine of angle between them. The result is coming as 8.03 kilonewtons. Now, once we have the resultant force, we still need to identify the angle. Here, for the triangle, we have an unknown angle theta between our force of 4 kilonewton and the resultant force. We can identify that angle by applying our sine law. That is sine of angle theta divided by the side of a triangle opposite to that angle theta. In this case, it is 6 equals to the sine of angle 105 divided by the side opposite to the angle 105. That is our resultant force of 8.03. Simplifying, we get the value of theta as 46.22. Since it is an angle between the force F1 and Fr, however, we are looking for the angle of resultant force from the positive u-axis, and the angle between the force F1 and the positive u-axis is 45 degrees. We can simplify and identify the angle from the positive u-axis to the Fr force by subtracting 45 degrees from 46.22. That gives us the final value of 1.22 degrees. In order to find the resultant force of a system of coplanar forces, we can start by dividing each one of the force into its rectangular components. So our force F1 of 850 Newton can be converted into F1x by multiplying it with the ratio of the triangle shown here of 4 divided by 5, whereas the vertical component along the y direction can be calculated by multiplying 850 with a ratio of 3/5. Next, our force F2, that is making an angle of 30 degrees with the vertical y-axis, can be converted into its rectangular components by taking the cos function of angle 30 degrees. That will create a component along the vertical axis, while the sine 30 will give us a component along the horizontal x-axis. Finally, I have a force of 750 Newton that is making an angle of 45 degrees with the y-axis, meaning that it will make the same 45 degree from the x-axis. So each one of those components along the x and y will be equals to one another, and they can be calculated by taking sine 50 cos of 45 or sine 50 sine of 45. Now, once we have all the components, let's go ahead and add them together to figure out the resultant forces. So adding all the component along the horizontal x-axis, we can start with our F1x that is pointed towards the positive x direction, so that's why it will be positive, whereas our F2x and F3x are in the negative x direction. So subtracting them, we get our resultant force of negative 162.8 Newton in the x direction. Similarly, we can repeat this process for all the components in the y direction. So here I have F1y in the negative y-axis, as well as f2y in the negative y-axis as well, whereas f3y is in the positive y direction. So adding them all give us the resultant of negative 520.9 Newton. Now once we have these two resultant components, we can combine them using our Pythagorean theorem and figure out our resultant force, which is coming 546 Newton. Now the angle of this force can be calculated by taking the tangent inverse of Fy over Fx. Here it is coming as 72.6 degrees. Now once we have the force and the angle, let's go ahead and plot the resultant force. Here the force Fx and Fy are both negative, meaning that they are in the third quadrant, and the angle 72.6 degrees is measured from the negative x-axis. Now in the question they are asking us to calculate the angle from the positive x-axis, so adding 180 to 72.6 give us our final angle, that is coming 253 degrees. In order to find the magnitude and direction cosine of the resultant force, we can first start by converting each one of those forces into its Cartesian coordinates. So to start, I have a force F1. It is on our x and z plane. So the x component can be calculated by multiplying 90 with 4 over 5, whereas the z component is calculated by multiplying the force 90 with 3 over 5. Here, the I and k are representing the unit vector along the x and z direction. Next, we have F2 force of 150 Newton that is acting in the 3D space. First of all, it can be projected along the xy plane by taking the cos 60 function of that force, whereas the sin 60 function will project it vertically along the z direction. Next, the component of the force in the xy plane needs to be further projected along the x and y direction. By taking the cos function of 45 degrees, it will project that component along the y direction, whereas the sine 45 function of the force will project it along the x direction. Now since we have 150 cos 60 sine 45 as the x component, it is represented by a unit vector I, whereas 150 cos 60 cos 45 is along the y-axis, so it is represented by a unit vector j, and finally the z component is represented by a unit vector k. Now for F3 force, since it is only acting along the z direction, we have just one component of it, that is 200k, representing the direction along the z-axis. Once we have all of these individual forces, let's go ahead and add all the I components together. It is giving us as 125.03. Next, we add the j components, and finally all the k components give us our final resultant force. Now in order to calculate the magnitude of the resultant force, we have to take the square root of all the square terms along the x, y and z axis and add them together. This gives us our magnitude of 407 newtons. Now for the direction cosines, it is given as cos inverse of the x component of resultant force divided by the magnitude of the resultant force. Taking cos inverse of that ratio give us our alpha value of 72.1. This is the angle this force is making with the x-axis. Respectively, beta is coming as 82.5. That is the angle it is making from the y-axis. And finally the gamma, the angle the force make along the z-axis, is coming as 19.5. Now finally let's go ahead and plot this force on the xy plane. Here the magnitude of the force will be given as 407, whereas the angle it makes from the z-axis is 19.5, with the x it is 72.1, and finally with the y beta it is 82. In order to find the resultant force and coordinate direction angle of the couple of forces acting along the line, we can start by first figuring out the point coordinates of the head and tail of the force vector. So to start, point A lies at a distance of 4 feet along the y-axis, so the point coordinates will be 0, 4, 0, whereas point B lies at a distance of 2 feet in the x direction and -6 in the z direction. Point C also lies on our xz plane at a distance of -2.5 feet, whereas the vertical distance can be calculated from the right angle triangle of 13, 12 and 5. Since 2.5 is half of 5, using the same ratio, the vertical distance will be half of 12. That will be 6 in this case. Next, we can go ahead and calculate the unit vector UAC, that is equals to the position vector divided by the magnitude of the position vector. The position vector is calculated by doing the head minus tail. So we subtract the point coordinates of C with the point coordinates of A and divide it with the magnitude of that position vector. Once we have the unit vector, multiplying it with the magnitude of the force, that is 80 pounds in this case, give us the force F1 in the Cartesian vector form. Now we will repeat the same process for our force F2 by calculating the position vector of RAB and dividing it with the magnitude of RAB to calculate the unit vector of AB. Once we have the unit vector, we will again multiply that with the magnitude of force F2 of 50 pounds to calculate the force F2 in the Cartesian vector form, that is coming as 13.4 I, negative 26.7 J, and negative 40.1 K. Now once we have both the forces in the Cartesian vector form, we can go ahead and add them together to figure out the resultant force in the Cartesian vector form. In this case, the I component will be added with the I component, the J component will be added with the J component, and the K component will be added with the K component. So our resultant force is coming as negative 12.8 I, negative 68.7 J, and 22.8 K. Now once we have the Cartesian form, we can go ahead and also calculate the magnitude of this force, because we will require that magnitude to calculate our coordinate angles. Now for coordinate angles, alpha, beta, and gamma are the angles that the force make along the x, y, and z axis respectively. So to calculate that, alpha is the cos inverse of the x component of the resultant force divided by the magnitude of the force, and it is coming around as 100 degrees. Similarly, we can calculate beta and gamma by utilizing the y and z component of the resultant force. In order to find the projection of force F1 on the line of action of F2, we can utilize the dot product between the force vector F1 with the unit vector of F2. So to start, force F1 needs to be converted into its Cartesian form, meaning that we need to identify its x, y, and z component. Since the vector is given in the 3D space, first of all, it is projected along the xy plane by taking the cos 30 function, whereas the sin 30 function will project it along the negative z direction. Now the 30 cosine 30 vector needs to be further resolved along the x and y component, meaning that if we take the cosine 30 of this vector, it will project it along the y axis, whereas the sine 30 is going to project it along the x direction. Once we have each one of these components, we can represent it in terms of I, J, and K component. Here the I, J, and K are representing the unit vector along the x, y, and z axis respectively. Simplifying, we are getting the value of 12.99 I plus 22.5 J minus 15K. Once we have F1, let's figure out our unit vector of force F2. So here the force F2 is making an angle of 60 degrees with the y-axis and 60 degrees with the z-axis as well. However, the angle with the x-axis is unknown. So first of all, let us solve for this angle alpha. As we know, cos square alpha plus cos square beta plus cos square gamma is equals to 1. Plugging in the value of beta and gamma equals to 60. We can simplify this and get the value of alpha. Here we are going to utilize the negative 0.707 terms to calculate the alpha, as it is greater than 90 degrees in this case. So the value of alpha is coming as 135. Once we have all the direction cosine of this force, we can write the unit vector by taking the cos function of each one of those angles. So our unit vector F2 is coming as negative 0.707I plus 0.5J and plus 0.5K. Finally, let's go ahead and take the dot product between the force vector F1 and the unit vector of force F2. Now for the dot product, we know that I dot I, J dot J, and K dot K is equals to 1, whereas the dissimilar components like I dot J or J dot K will give us the value of 0. In other words, the I components will be multiplied together, then the J components will be multiplied together, and finally the K components will be multiplied together. This gives us our final value of negative 5.44 pounds. Here the negative sign is indicating that the sense is opposite to the direction of force vector F2. In order to find the force in each chord for the 60 kg bucket to be in equilibrium, we can start by first drawing the free body diagram of the bucket itself by placing the origin at point F. Here we have two forces. One is the weight of the bucket that is acting vertically downward. The other is the tension in the rope going away from point F. We can apply our equilibrium equation along the vertical direction to solve for the force in the rope, that in this case will be equals to the weight of the bucket as 589 Newton. Next, we can consider point A and apply the free body diagram of point A by placing the origin at that particular point. In this case, I have three ropes that is connected to point A. All are taken in tension going away from point A. The value of FAF is already known, whereas the value of FAC needs to be divided into its horizontal and vertical component. We can do that by utilizing the dimension given to us, as the horizontal distance from point A to C is 3 meter and the vertical distance from point A to C is 4 meter. Utilizing the right angle triangle and the Pythagorean theorem, we can identify the length of this rope as 5 meter. Next, let's apply the equilibrium condition. So doing summation of forces along the y-axis equals to 0, we will have a component of force FAC along the vertical direction that will be obtained by multiplying it with 4 over 5. Subtracting it with the weight of the bucket will give us the value of force FAC. Next, we can do the summation of forces along the horizontal direction equals to 0. Here also we have a horizontal component of the force FAC, which we can obtain by multiplying the force with 3 over 5. That is in the negative direction based on our reference point we have selected, whereas FAB will be in the positive direction. Simplifying, we get the value of FAB equals to 441 Newton. Finally, we can go ahead and draw the free body diagram of point C by placing the origin at that particular point. Again, there are three cars that are going away from point C, all in tension. We have already figured out the value of FAC, so the other two can be calculated by applying our equilibrium condition along the x direction and the equilibrium condition along the y direction, which give us our value of FCD as 441 Newton, whereas the value of FCE is coming as 589 Newton. In order to find the force in each cable needed to support the 500-pound crate, we can start by drawing our free body diagram for joint A by placing the origin at that particular point. Here, three cables are connected to point A, starting with the crate that has a weight of 500 pounds. Next, we have a cable from A to C making an angle of 20 degrees from the horizontal x-axis, whereas the cable A to C makes an angle of 35 degrees with respect to the negative x-axis. Once we have all the forces listed, let's go ahead and apply the equilibrium condition by adding all the forces along the x-axis. Here, only two components of the force FAC and FAB act along the positive and the negative direction. So we can figure out a relationship of FAB in terms of FAC. Next, we can go ahead and do the summation of forces along the z-axis. Here, the weight of the crate is acting vertically downward. That's why it is taken as negative, whereas the component of force FAC and FAB will be pointed in the upward direction. We can calculate those components by taking the sine function of 20 degrees and sine function of 35 degrees. Simplifying, we get the value of FAC as 574 pounds. Next, we can go ahead and place that information in equation 1 and solve for FAB, that is coming as 500 pounds. Once we have those values, now we can go ahead and draw our free body diagram for joint C. We have already calculated the force from C to A, that is 574 pounds. That is making an angle of 35 degrees with respect to the horizontal x-axis. The other two cables that are acting downward from C to E and C to F, their length can be calculated using our Pythagorean theorem, which is coming as 25 feet. Similarly, we can calculate the length from C to D using the Pythagorean theorem as well, that is coming as 26 feet. Once we have all the dimension, we can go ahead and start applying our equilibrium condition, starting with summation of forces along the x-axis. So our 574 pound force, the cost function of that will give us the component along the positive x-axis, whereas the FCD, if we multiply that with 10 over 26, will give us the component along the negative x direction. Simplifying, we get the value of FCD. Next, we can go ahead and apply the equilibrium condition along the y direction. Here, only two components of the force FCE and FCF are acting along the positive and negative y direction. That makes those two forces equals to one another. Finally, we can apply the summation of forces along the z-axis. So for them, the two components of FCE and FCF is going vertically downward by multiplying them with 24/25, whereas the 574-pound force, if we take the sine 35 function, it's also going in downward direction. Whereas the z component of FCD will be positive as it is pointed in the upward direction, which can be calculated by multiplying it with 24/26. Simplifying, we can calculate the value of FCF, that is coming as 416 pound. Since that is equals to FCE, that value is also 416 pounds. In order to find the moment of forces about point A, we can start by establishing our sign convention. In this case, I'm considering counterclockwise moment as positive. Next, let's look at our force F1 having a magnitude of 375 acting vertically downward. Now, the moment arm this force make with point A is 8 feet. Multiplying the force with its moment arm will give us the magnitude of the moment. Next, we also still have to establish either it is making a clockwise or counterclockwise moment. Since the force is acting downward and the moment arm is to the left of the force, it is going to make our clockwise moment. Next, let us look at force F2 that is acting in an angle. So we can go ahead and first resolve it into its vertical and horizontal component. We can do that by utilizing the information in the right angle triangle. So in this case, the hypotenuse of a right angle triangle is given to us as 5, whereas the opposite is 4. So multiplying 500 with 4/5 will project it along the vertical axis. This is basically the sine theta that we are multiplying 500 with. Similarly, we can project it along the horizontal axis by multiplying 500 with 3/5. Once we have the components, let's go ahead and figure out what moment they make. So starting with the horizontal component, since the force vector is in the line of action of point A, it is not going to create any moment or any turning effect. This force vector is basically pushing point A. Next, the vertical component will make our moment having a moment arm of 14 feet. Again, this is making our clockwise rotation. Finally, let's resolve our force F3. We are given an angle of 30 degrees from the vertical, so we can project it along the vertical direction by taking the cos 30 function. Whereas in order to get the horizontal component, we are multiplying the force with sine 30. That will give us the horizontal component. Once we have the component, let's figure out the moment. So the moment created by the vertical component will still be in the clockwise direction, having a moment arm of 19 feet. However, the horizontal component of force F3 is going to make our counterclockwise moment. In this case, the moment arm is 0.5 feet. Now, once we have all the moments figured out, let's add them all together. Simplifying, we get the value of negative 11,192.7 pound-feet. Since we have considered the counterclockwise moment as positive, the negative sign is indicating that the resultant moment acting at point A is in clockwise direction. Moment of a force about a point can be calculated by taking the cross product of the position vector and the force vector. The position vector will initiate at the point at which we want to calculate the moment, and its head will be at the location where the force is applied. Here the position vector is RAC, which we can write by taking the difference between the point coordinates of C and A, which is coming 0.55 pi plus 0.4 j and negative 0.2 k in meters. Next, we need to write the force vector in Cartesian vector notation by resolving it along the x, y, and z axis. First, we will consider the right angle triangle with an angle of 30 degrees and resolve the 80 Newton force vector along the other two sides of the triangle by taking the sine and cosine of 30 degrees. This gives us a component of the force along the negative z-axis and a component in the xy plane. Now, this component in the xy plane needs to be further resolved using the second right angle triangle of 40 degrees. Taking the cosine of 40 degrees will project it along the y-axis as 40 degrees is measured from the line parallel to the y-axis, and the sine function will project it along the axis parallel to x. Simplifying it gives us the value of force of 44.5 I plus 53.07 J and 40 K newtons. Next, to calculate the moment, we need to take the cross product between the position vector and the force vector. One important point to remember while taking the cross product is that cross product does not follow the commutative law, which means that R cross F won't be equals to F cross R. Finally, simplifying the cross product, we get the moment value of negative 5.38I plus 13.1J and 11.38K Newton meters. In order to find the moment of a force having a magnitude of 80 pounds acting vertically upward about the x-axis, we first need to identify our reference axis. Here I'm considering x prime, y prime, and z as the reference axis. Next, let's go ahead and write our triple scalar product. That is a product between three vectors that give us an scalar quantity. Starting with the very first vector is the unit vector of the direction across which we are calculating the moment. Next, I have a position vector r that starts from any point on the direction at which we are calculating the moment and heading towards the line of action of the force. And finally, we have the force vector. Next, let's go ahead and identify the unit vector of axis x. Since our reference axis is x prime and y prime, so I need to project our axis x along x prime and y prime, which we can do that by taking the cos 30 and sin 30 function respectively. Next comes the position vector. Since the idea of the position vector is it still should be on the axis, in this case, I'm selecting point A as it lies on the x-axis as well, whereas it should be on the line of action of the force. So in this case, we are considering point C as that head. So the required position vector in our case will be RAC. To get that, we can identify the point coordinates of C. So since the length of that A frame is of 6 feet, but it is tilted at an angle of 15 degree on our Z and X prime plane. So in order to get our X prime component, we are taking the cos 15 function of 6, but since it is acting in the negative direction, that's why I have minus 6 cos 15, whereas the component along the y prime direction of point C is 3 feet, and the z component can be calculated by taking the sine 15 function. So the z component is 6 times sine 15. Once we have that, we can do head minus tail and identify our position vector RC. Finally, I have our force vector that is acting vertically upward along the z-axis. So in terms of Cartesian form, the force vector is represented as ATK. Once we have all the three vectors, let's go ahead and plug that information in our expression. So our triple scalar product can be calculated using a determinant function in which the first row represents the unit vector of the axis across which we are calculating the moment, whereas the second row is our position vector and the third row of that determinant is the force vector. Next, we can go ahead and simplify that determinant to get our final moment that is coming as 440 pound-feet. In order to find the magnitude of the resultant couple moments of the two moments shown in the figure, we can go ahead and start resolving these moments into its x, y, and z component and then add them together to figure out the resultant couple moment. So our m1 is making an angle of 20 degrees with respect to our xy plane. So taking the cos 20 function will project it along the xy plane. Now, in order to further resolve it along the x-axis and y-axis, we know that this line is making an angle of 15 degrees with respect to the y-axis. So taking the cos 15 function will project it along the y-axis, whereas if we take the sine 15 function, it will project it along the x-axis. Finally, we need to identify the component along the z-axis. So 40 multiplied with sine 20 will project it along the z-axis. However, since this is acting in the downward direction, and that's why it will be taken as negative. Also, the rotation is happening in the clockwise direction. So by convention, counterclockwise is taken as positive and clockwise is taken as negative. Simplifying, we get the value of m1 as 9.72i plus 36.31J and negative 13.68K. Next, let's go ahead and resolve our M2 moment. Here, the moment lies on the XY plane and it is making an angle of 30 degrees with respect to the Y-axis. So if we take the cos 30 function, it's going to project it along the Y-axis, whereas the sine 30 function will project it along the X-axis pointing towards the negative direction. Here again, the moment is happening in the clockwise direction. That's why we have a negative I component here, whereas it is in the counterclockwise direction along the Y-axis. That's why multiply, I have the positive component. Simplifying, I get the value of m2 as negative 15I plus 25.98j. Now to figure out the resultant couple moment, we are just going to add them together. So I component will be added with the I component, j component is added with the j component, and k added with the k component, giving us our resultant couple moment in the Cartesian form. Now to calculate the magnitude, we can utilize the magnitude formula, that is the square root of the x component square plus y component square plus c component square. This gives us the value of 64 pound-feet. Now, once we have the magnitude, let's go ahead and identify the coordinate direction angles the resultant couple moment is making with respect to x, y, and z axis. So to calculate with respect to x-axis, we have our alpha, that is equals to cos inverse of the x component of the resultant couple moment divided by its magnitude. That gives us an angle of 94.7. Similarly, if we take the cos inverse of the y component, it is going to give me an angle with respect to the y-axis, and if we take the z component divided with the magnitude and take the cos inverse, it's going to give me the angle it is making with respect to the z-axis. In order to replace the forces acting on the truss by a single force and a couple moment acting at point C, we can start by resolving the forces in its x and y component and then combining them together to figure out the resultant force. So to start, our 500 pound force is acting at an angle given by the right angle triangle. To calculate its x component, we can multiply the 500 with 4 over 5. This will give us the x component of the 500 force equals to 400 pound. Next, we can go ahead and add all the y components of the forces acting on the truss. In this case, starting with the 500 pound, if we multiply it with 3 over 5, it is going to give me the y component. In this case, it is pointing downward, so that's why we will take it as negative. Similarly, our 100 pound force, 150 pound force, and 200 pound force are all acting in the negative y direction. So adding them all together give us the resultant force in the y direction as negative 750. Here the negative sign is indicating it is acting downward. Now to calculate the resultant force magnitude, we can apply our formula of a square root of x component square plus y component square. This is give us the final value of 850 pound. Now in order to identify the direction of the resultant force, we can use the tan inverse formula, that is taking a tangent inverse of the y component's magnitude divided by the x component magnitude, which gives us an angle of 61.9. Now to represent it at point C, since our x component is going towards the right and y component is going downward, it makes our force in the fourth quadrant, and the angle is measured in the clockwise direction from the positive x-axis. Next, let's go ahead and figure out the resultant couple moment at point C. That will be equals to the sum of moment of all the forces acting on the truss with respect to point C. So we can go ahead and start with our 200 pound force acting downward and have a moment arm of 2 feet. This force is going to create our clockwise moment as the moment arm is towards the left of the force. Similarly, 150 pound force and 100 pound force are going to create our clockwise moment. That's why they are taken as negative. Next, I have our 500 times 4 over 5 that is applied horizontally. So the moment arm is in the vertical direction of 6 feet. This force is going to create our clockwise moment as well. Finally, we have our 500 times 3 over 5 force that has a moment arm of 8 feet. Again, this is going to make our clockwise moment. So adding them all together, we get our final value of negative 6,400 pound-feet. Here the negative sign is indicating that the moment is in clockwise direction. In order to replace the loading acting on a beam by a single resultant force and to figure out its location with respect to point A, we can start by first figuring out the resultant forces component along the x and y direction. So to start, our 450 Newton is making an angle of 60 degrees with respect to the x-axis. So the cos function will project it along the x direction, whereas our 700 Newton is making a 30-degree angle with respect to the vertical y-axis. So we have to take the sine 30 function in order to project it along the horizontal x-axis. Adding them together give us our final component as 125 Newton that is directed towards the right. Next, we can do the summation of forces along the y direction to figure out the resultant force y component. In this case, again, our 450 is making an angle of 60 degrees with respect to the horizontal. So taking a sine 60 function will project it downward direction. Then I have 300 Newton that is acting vertically downward, whereas our 700 Newton, if we take the cos 30 function, will project it downward. Adding them all together give us our y component as 1296 Newton. Next, we can calculate the resultant force by using the magnitude formula, that is the square root of x x component square plus y component square. This gives us the resultant force magnitude as 1302 Newton. Next, to figure out the angle, we can utilize our tan inverse function by taking the tangent inverse of the y component magnitude divided by the x component magnitude. This gives us an angle of 84.5 degrees. Now, since both the x component and y component has negative sign, it means that it lies in the third quadrant. Next, we can go ahead and figure out the location of this resultant force with respect to point A by drawing the force on the beam itself. Since the force magnitude is 1302 and making an angle of 84.5, this can be drawn on the beam. Next, this position, let's give us an unknown value of x that we are going to solve for. To calculate this x value, we can utilize our moment at point A of the resultant force and equate it to the summation of moment by all the individual forces. So in this case, our resultant force y component is only going to create the moment about the A point, whereas the x component is not going to create any moment since it's passing along the line. So the resultant force moment with respect to point A will be 1296 times x, whereas for the individual forces component, only the y component in this case is going to create the moment, as the x component of all these forces are passing through the line of action of point A. So our 450 sine 60 have a moment arm of 2 that is making a clockwise moment. Similarly, 300 Newton force is also making a clockwise moment with a moment arm of 6 meters, whereas 700 cos 30 Newton force is also making a clockwise moment with a moment arm of 9. Finally, I have an external couple moment acting at the very end of the beam, having a value of 1500 Newton meter, also going in the clockwise direction. So adding all of them together and solving for x, we get our final value of the position our resultant force is making with respect to point A as 7.36 meters. In order to replace the loading acting on a beam with an equivalent resultant force and specify its location, we can start by converting the distributive loading into known shapes and then calculating the areas of these shapes. These areas basically convert these distributive loading into a point load. So to start, I have a rectangular shape having a width of 9 meters and a height of 2 kilonewton per meter. Multiplying the two will give us a point load of 18 kilonewton that is acting in the middle of the rectangle. Next, I have a right angle triangle with a base of 6 meters and an altitude of 5 minus 2 kilonewtons. This basically gives us the area equals to half time base times altitude equals to 9 kilonewton. Next, the position of this point load will be acting at a centroid of a right angle that is equals to 1/3 of the base measured from the higher end of the right angle triangle. Next, I have another right angle triangle on the right, in which we can again calculate the area by half times base times the altitude of the right angle triangle. That gives us the value of 3 kilonewton. Now this point load is acting again at the centroid that from a lower end is measured by 2/3 of the base. That's why it is equals to 2 meters. Next, adding them all together give us a final resultant force of negative 30 kilonewton. Here the negative sign is indicating that the force is pointed downwards. Once we have the resultant force, let's identify the position on the beam. So to start, we can draw the resultant force on the beam and specify a distance x with respect to point O, as we are solving for this variable x. Now to calculate the value of x, we can utilize our summation of moment of the resultant force with respect to point O, that will equals to the sum of moment of all the individual forces with respect to point O. So to start, our 30 kilonewton will make a clockwise moment with a moment arm of x, whereas the 9 kilonewton, 18 kilonewton, and 3 kilonewton, all of them will make a clockwise moment as well, with the moment arm of 2 meters, 4.5 meters, and 8 meters respectively. Simplifying, we get our value of x as 4.1 meters. In order to find the support reactions at a roller, rocker, and a contact the beam mates at a smooth plane at A, we can start by developing our free body diagram. Now for the free body diagram, it has all the external loads acting on it. Other than that, all our support reactions are listed. So at rocker, since we have just one support reaction acting vertically upward, that's why it is given as RC. Whereas for the roller, again, we have one support reactions as it limits the motion in the vertical direction. That's why I have a force going upward given as RB. Finally, for the smooth plane, since the plane is at an angle, our support reaction will be normal to the plane, meaning it is making a 90-degree angle with respect to the plane given here. So since we are given a right angle triangle of 3, 4, 5, similarly, our support reaction will be of the right angle triangle as well, 3, 4, 5. The only thing will be the 3 and 4 will swap its position because they are perpendicular to the plane shown. Once we have the free body diagram, we can go ahead and start applying our equilibrium equations. So to start, we can do summation of forces along the horizontal x direction equals to 0. In this case, support reaction Ra has an x component that we can calculate by multiplying it with a ratio of 3/5. Next, I have a x component of 800 Newton force that is making an angle of 60 degree with the horizontal x-axis. So taking the cos 60 function will give us the x component. Simplifying, we get our value of Ra as 666.7 Newton. Next, we can go ahead and write our other two equilibrium equations. Now, in this case, you have to be careful which equations to pick. So if I do summation of forces along the vertical z direction, I will have two unknowns. So it's better to write our moment equation first. So for that purpose, I'm writing summation of moment at point C equals to 0. That will eliminate my unknown of RC. So writing all of our forces that is going to create the moment about point C is starting with the vertical force of Ra that has a moment arm of 12. It is going to make our clockwise moment. That's why given as negative. Similarly, the support reaction Rb is also making our clockwise moment, whereas the 500 Newton force acting downward is making our counterclockwise moment. That's why it is positive. Finally, I have my vertical component of 800 Newton that is calculated by taking the sine 60 function, multiplying it with a moment arm of 6. That is going to create our counterclockwise motion. Simplifying, we get our value of Rb as 219.6 Newton. Finally, we can go ahead and write our summation of forces along the vertical direction equals to 0. In this case, we are going to add all the forces going in the upward direction and subtract all the forces going downward. Simplifying, we get our value of Rc as 440 newtons. In order to find the support reactions at the ball support at point B and C and a ball and socket joint at point A for a uniformly loaded plate as shown in the figure, we can start by developing our free body diagram. Now for the free body diagram, first of all, we have to identify our reference point such as X, Y, and Z axis, and next list down all the external loads acting on the plate as well as the support reactions. So to start, for a ball and socket joint, we have three support reactions going along the X, Y, and Z axis as the motion is restricted along X, Y, and Z axis for a ball and socket joint and the rotation is allowed. Next, for the ball supports at point P and C, we have just one support reaction acting vertically upward as the motion is restricted along the Z axis. Next, let's go ahead and identify the position of these support reactions because we will need these distances to calculate the moment while we are writing our equilibrium equation. Afterwards, we have an external load that is uniformly distributed on the plate. Let's go ahead and convert it into a point load by multiplying that distributed load with the area of the plate that is coming as 16 pounds. Now this point load will act at the centroid of the plate, and the dimensions we can list them down on the free body diagram as well. Once we have all the external loads and support reactions, let's go ahead and apply our equilibrium condition. So for a 3D system, we have 6 equilibrium conditions. We can start by summation of forces along the x-axis equals to 0 and summation of forces along the y-axis equals to 0. Since we don't have any other force acting along the x and y axis except ax and ay, the value of them is equals to 0. Next, we can write the summation of moment about the x-axis equals to 0, taking counterclockwise as positive, since it's only going to give us two unknowns, as ax, ay, and az won't create the moment about the x-axis as they'll pass through the axis itself, whereas cz will create our counterclockwise moment with a moment arm of 1 feet, whereas BZ also going to create a counterclockwise moment having a moment arm of 2. Finally, our point load of 16 pounds is going to create our clockwise moment with respect to x-axis. Next, we can go ahead and write summation of moment along the y-axis equals to 0. Similarly, ax, ay, and az won't create moment. Only cz, bz, and 16-pound force is going to create the moment. Simplifying these two expressions, we can calculate the value of cz and bz that is coming as 5.33 pounds. Now, once we have the ball support reactions at B and C, we can go ahead and identify our az value. To do that, we can go ahead and write our summation of forces acting acting along the z-axis equals to 0. In this case, AZ is pointing upward, that's why it's taken as positive. Similarly, our BZ and CZ is acting in the upward direction, whereas 16 pound is going downward. Simplifying, we get the value of AZ as 5.33 pound as well. In order to find the force in each member of the truss, we can utilize our method of join by drawing the free body diagram of each one of them and identifying the loads in the member. So to start, our joint A has an external load of 130 pounds that is applied at an angle, whereas it is connected to a member AB and AC. In this case, on the free body diagram, I always go ahead and draw the forces in the tension direction. And if we get a negative number, that means that the member is in compression. So for our summation of forces along the vertical axis, we are getting an FAC value of negative 150 pounds. That means that the member is in compression. Whereas if we do summation of forces along the x direction, we are getting a value of FAB equals to 140 pounds. This means that the member is in tension. Now next, move to joint B. Here we have one of the member as zero force member, and we can prove it using the free body diagrams. Since two of the members are collinear and there is no external load or support at point B, so the third member that is not collinear is going to be a zero force member. By doing summation of forces along the y-axis, we can see that the force FPC is equals to 0, whereas summation of forces along the x direction is giving the force in member BD as 140 pounds in tension. Next, we can move to joint C and repeat the same process of drawing the free body diagram and list down all the unknown loads and the known loads as well. In this case, since the member CA was 150 pound in compression, that's why it is given as negative 150. Applying the equilibrium equation and simplifying, our FCD is coming as 150 pound in tension, whereas the value of FCE is coming as negative 180 pound. This negative sign is indicating that the member is in compression. Next, let's move to joint D. Here you can see that it is connected to 4 members. So whenever we are selecting the joint, we have to make sure that it has no more than 2 unknowns, because we only have 2 equilibrium equations to solve for these unknowns. Simplifying, we are getting the value of FDE as negative 120 pound, meaning that the member is in compression, whereas member DF is in tension, having 230 pounds. Finally, let's move to joint E and draw the free body diagram. Applying the equilibrium condition along the x direction, we get our final member load as negative 300 pound. Again, the negative sign is indicating that the member EF is in compression. In order to find the forces in truss members HI, FI, and EF, we can utilize the method of section, in which we basically make a cut along the members in which we are interested in, and then separate the structure into 2 halves. Here we have created a section along the 3 members HI, FI, and EF. Now we can pick any one of those 2 halves in order to figure out the reactions along those members. In this case, we will be interested in picking the smaller half, since it will be easier to solve. Now, along those halves, we have a support reaction at G, that is a roller, and we need to first identify what are those support reactions. So let's consider the whole structure and write our equilibrium equation. In order to find the support reaction at G, I can write the summation of moment at point A equals to 0 and solve for G of Y, which is coming 12.66 kilonewtons. Now let's go ahead and draw the free body diagram of the smaller section. Since here we have made a cut along the members HI, FI, and EF, the internal forces will become exposed. Since it is a truss that is a 2-force member, so we will only have the force acting along the axis of these members as F of HI, F of FI, and F of EF. Other than these internal forces, I have one external force of 6 kilonewton that is applied at point F, and then we have a support reaction at G that we have calculated as 12.66 kilonewtons. Now once we have identified the forces, we can also identify the direction of the 2 forces acting along the axis of these members. So for force F of I, since the base of the triangle is 2 and the perpendicular distance is 3, so the hypotenuse can be calculated using the Pythagorean theorem, that is coming 3.6. Next, we have that force F of HI. It is making a triangle of 3, 4, and 5. Since everything has been identified, let's go ahead and write the equilibrium equation. I can start by writing the summation of moment at point F equals to 0, taking counterclockwise as positive. Here we have a support reaction at G that will create a counterclockwise moment with a moment arm of 2. Next, we have forces 6 kilonewton, force in the member EF, and force in the member FI. These 3 forces won't create any moment since they are passing through the point F. Next, the only other force that that will create a moment is the horizontal component of force FHI that has a moment arm of 1.5. So adding these two forces and equating it equals to 0, we get the force in the member HI equals to negative 21.1 kilonewton. Now the negative sign is indicating that the direction that we have picked is the opposite direction in which the force is being applied. Since we have picked the direction in tension, the force is compression in our member HI. Next, I can write the summation of forces along the y-axis equals to 0. In this case, we have a vertical component of force FHI that can be calculated by multiplying our negative 21.11 to 3 over 5. Then I have a 6 kilonewton going downwards. Then I have a 12.66 kilonewtons at G going in the upward direction. And finally, I have a vertical component of force F of I that can be calculated by multiplying the magnitude of force by 3 over 3.6. Simplifying, we get the force along the members Fi as 7.2 kilonewton. Finally, we can figure out the force in the member EF by writing summation of forces acting along the horizontal direction equals to 0. Here, other than the force EF, we will have the horizontal component of force in the member F of I that we can calculate by multiplying 7.2 to 2 over 3.6, and also the horizontal component of force in the member HI, which we can find by multiplying the force magnitude of negative 21.11 to 4 over 5. This gives us the force in the member EF as 12.88 kilonewton. In order to find the forces in truss members, we can apply the method of sections. Here we are looking for forces in member DC, HC, and HI. So we have to apply a cut along those members and divide the structure into two halves. Now we can pick any one of the halves to identify the forces along those members. In this case, each one of the halves have a support reaction. So first of all, we have to find the support reactions for the half that we pick. Here I'm going to select the half with the support reaction at point A. So let us figure out our AX and AY. To do that, we can apply the equilibrium equation. Summation of forces along the x-axis equals to 0. This gives us the value of AX equals to 70 kilonewton. Next, we can apply the summation of moment along point F and equate it equals to 0. The reason why we are doing it at point F is so that our force Fy won't create any moment, and we will be able to figure out the force Ay that is coming 32.5 kilonewton. Next, we can go ahead and draw the free body diagram of the selected section. Since we have made a cut along the members CD, CH, and HI, the internal forces along those directions will become exposed, and they are shown here in tension. We can also identify the direction of force in member CD from the right angle triangle that has a ratio of 3:4:5. Other than the internal forces, we have a couple of external loads applied at point C and at point B, and we have the support reactions at point A. Once we have developed our free body diagram, let's go ahead and write the equilibrium equation. We can start by writing the summation of moment equation about point C and equating it equals to 0. Since the 30 kilonewton force, the force in the member CH, and the force in the member CD are all going through point C, they won't create any moment with respect to point C. The only unknown force that is going to create a moment with respect to point C is the force in member HI, which can be calculated from this expression. It is coming 42.5 kilonewtons. Summation of forces along the vertical direction and equate it equals to 0. Here we have that 42.5 kilonewton going in the tensile direction in member HI. We also have a support reaction of 32.5 kilonewtons going upward, and we also have our force FCD. The vertical component of that can be calculated by multiplying it with 3/5. Simplifying, we get a value of negative 1.25 kilonewton. Here the negative sign is indicating that the force in the member is in compression. Finally, we can write the summation of forces along the x direction and equate it equals to 0 to figure out our forces in the member CH that is coming 100 kilonewtons. Since it's a positive number, the force is in tension. In order to figure out the force P required to hold the 100-pound weight in the equilibrium position for the pulley system as shown in the figure, we can start by developing the free body diagram of pulley A to calculate the tension in the rope connecting pulley A, which is linked to pulley B and pulley C. Eventually, we can calculate the load P required to keep this thing in equilibrium. So to start, for our free body diagram of pulley A, the weight of 100 pounds is acting vertically downward, and I have two ropes going in the upward direction. Now for the rope, the force will always be in tension. That's why they are going away from the pulley, given as TA. Next, we can apply the equilibrium condition to solve for this tension that is coming as 50 pounds. Now, next move to our pulley B and develop the free body diagram. Now, in this case, the rope that is connecting pulley A and pulley B, the tension in that we have calculated as 50 pound, whereas I have two ropes going in the upward direction at pulley B. This tension can be again calculated by applying the equilibrium equation along the vertical axis. That gives us the value of tension as 25 pound. Finally, let's go ahead and draw the free body diagram of pulley C. The rope that is connecting pulley C and pulley B is in tension of 25 pounds, whereas the rope that is extending from pulley C towards pulley D is the same rope, so the value of tension will be constant throughout this rope. That's why I have two forces P going in the upward direction, going away from the pulley C. Applying the equilibrium condition and simplify, we get our value of P as 12.5 pounds. In order to determine the force that the pin C and D exert on member ECD of the frame, we can start by developing the free body diagram of the member ECD and listing down all the external loads and the support reactions exerted on the member. To start, I have a horizontal load of 800 pound acting in the X direction, whereas at point C and D we have our pin support. Now for point D, I have the two support reactions Tx and Ty for the pin, whereas the member CB is a two-force member, so the force will be exerted along the axis of the member and can be represented by FCB along the axis. Now we can identify the direction of that axis by the right angle triangle given by a base of 1 feet and the perpendicular distance of 2 feet. It is giving us the hypotenuse of root 5. Next, we can identify the position of point C with respect to D and list down its distance from point D of 2 feet in the vertical and 2 feet in the horizontal direction. Once we have listed all the external loads and support reactions and the dimensions, we can go ahead and start applying our equilibrium equation. Now to start, we can apply our summation of moment at point D equals to 0. This will eliminate both dx and dy as they are not going to create any moment. Next, the force FCB can be divided into vertical and horizontal component, and we can identify the moment these forces create with respect to point D. So to start, the vertical component of force FCB can be calculated by multiplying it with a ratio of 1 over root 5. Here the moment arm is 2 feet and it is creating our clockwise moment. That's why it is given as negative. Whereas the horizontal component is calculated by multiplying it with 2 over root 5. Again, the moment arm is 2 feet and it is creating our clockwise moment as well. Finally, the 800 pound of external load is creating our counterclockwise moment. Simplifying, we get our value of FCB as 1788.8 pounds. Next, we can go ahead and apply our summation of forces along the horizontal axis equals to 0 and simplify to get our value of dx, which is coming as 800 pounds. Finally, we can apply our summation of forces acting along the z direction equals to 0 and add all the loads acting along the z direction. Here I have FCB component going vertically upward that can be calculated by multiplying 1788 with 1 over root 5, plus I have my dy going upward on my free body diagram. This gives us the value of dy as negative 800 pounds. In order to find the internal loads at point D on the structural member, what we can do is draw an imaginary line and divide the beam into two halves. Next, we can select any one of the halves to solve for the internal loads. Here we are going with the section DB. Since we have a support reaction at point D, we need to identify those forces. So let's go ahead and draw the free body diagram of the whole structure and first identify the support reactions Px and Py. Here we have a rectangular distributive load of 250 pounds per foot that can be converted into a point load by multiplying it with the 18 feet of the span of the beam. That is coming 4.5 kilopounds. Next, I have a roller at point A that will have vertical support reaction. And finally, we have an external load of 4 kilopounds in the horizontal direction. Once we have the free body diagram, we can go ahead and start applying the equilibrium equation. So starting with summation of forces along the x-axis equals to 0, we have only one force acting along the x-axis of 4 kilopounds. So that will be equals to our Px. Next, we can go ahead and write summation of moment equation at point A equals to 0. Since we are doing the moment at point A, the force Ay won't contribute to the moment as it's passing through the line of action. we have our external load of 4 kilopounds that have a moment arm of 3 and making our counterclockwise movement, whereas the distributive load that is converted into a point load of 4.5 kilopounds have a moment arm of 1 and that is making our clockwise movement. Finally, we have By that has a moment arm of 10. Simplifying, we get the value of By as negative 0.75 kilopounds. Now, once we have identified the support reactions, let's go ahead and draw the free body diagram of our section and solve for the internal loads. Since Bx was 4 kilopounds to the left and By was negative 0.75 kilopounds going upward, now the distributive loading can be converted into a point load. Since we have a bit of 4 feet, that 250 pounds per foot is equals to 1 kilopounds. Now at the cut, we will have 3 internal loads, N as normal, B as shear force, and our couple moment of M. Once we have the free body diagram, we can go ahead and start applying the equilibrium equation to solve for these unknowns. So starting with summation of forces along the x-axis equals to 0. Here we have just one unknown in x direction. So our normal force is equals to negative 4 kilopounds. Next, we can go ahead and write summation of forces in the vertical direction equals to 0, which give us our value of shear force equals to 1.75 kilopounds. Finally, we can do the summation of moment at the cut and solve for our couple moment MD. Here, the point load of 1 kilopound with a moment arm of 2 will create our clockwise moment. Next, we have a force of negative 0.75 kilopounds with a moment arm of 4 that is creating our counterclockwise moment. And finally, we have our couple moment MD in the clockwise direction. Simplifying, give us the value of MD as negative 5 kilopounds fit. In order to find the internal loads in the structural member at a specific point, all we need to do is to create an imaginary cut at that specific point and divide the member into 2 separate pieces. Now for analysis, we can pick any one of those halves and solve for the internal loads. Typically, we select a half that have least amount of unknowns. So in this case, I'm going to pick the left hand side, as the right hand side have a roller at A and a pin at point B. So let's go ahead and draw the free body diagram. Now at the specific cut, 3 internal loads will become exposed. We have a horizontal force of normal given as NC, a vertical force that is our shear force given as VC, and a couple moment given as MC. Now once we have our free body diagram, let's go ahead and apply the equilibrium conditions. Here, starting with summation of forces along the x-axis, I have just 2 forces, one an external load of 4 kilopounds and our normal force NC in the horizontal direction. This gives us the value of normal force as negative 4 kilopounds. Now one thing to keep in mind, the negative sign is just indicating the direction of the force. So in actual case, the normal is acting in the opposite direction in which we have drawn on our free body diagram. Similarly, we can do summation of forces in the vertical direction that give us the value of our shear force equals to negative 1 kilopounds. Finally, we have our summation of moment equation that we can write on any point on the structural member. However, we select the summation of moment at the cut so that the normal force and the shear force won't contribute into the moment equation. Here I have an external load of 4 kilopounds that is making a counterclockwise moment having a moment arm of 3. Next, we have our distributive load that is converted into a point load having a moment arm of 2 feet that is also producing a counterclockwise moment. And lastly, we have our couple moment MC, equating it to 0, give us its value of negative 14 kilopound fit. In order to figure out the shear force and bending moment diagram, the very first thing we have to do is to figure out the support reactions. Here we have a support of roller at point A and a pin at point B. Since rollers provide supports in the vertical direction, so we have a force acting vertically upward as AY, whereas pin provides supports in both horizontal and vertical direction. However, since all the loads are acting vertically downward, we will have the support reactions only going vertically upward as BY. Next, we can convert the distributive loading into a point load by multiplying 4 kilopounds per foot times 30 feet. That will give us 120 kilopounds. Next, we can apply the equilibrium equation as summation of forces acting along the y direction equals to 0 and add all the point loads. This gives us AY plus BY equals to 160. The second equilibrium equation can be written as summation of moment at point A equals to 0, which give us the value of Ey as 80 kilopounds. Plugging that information in equation 1 give us the value of Ay that is also coming at 80 kilopounds. Next, let's draw the free body diagrams. To draw the shear force diagram, we can utilize the loads acting on the beam. To start, we have a 20 kilopound load acting vertically downward that will cause a jump down from 0 to negative 20 on the shear force diagram. Next, we have a support reaction of 80 kilopound that will cause a jump up from negative 20 to 60 kilopounds. After that, we have a distributive loading acting vertically downward. The area under the distributive loading is coming around 120, meaning that from 60, 120 is subtracted. That makes our value on the shear force diagram to negative 60 at point B. Now, to figure out what will be the slope from point A to point B, we have to recall that we integrate the area. So we have a slope of 0 for a uniformly distributive loading. While we integrate that, it's converted into a linear relation. So from 60 to negative 60, we will have a linear profile. After that, we have a point load of 80 kilopounds that will cause a jump up. So from negative 60 plus 80, that will leave it to 20 kilopounds. Next, we have a point load acting at the very end of 20 kilopound, acting downward, that will cause a jump down from 20 to 0. Now to draw the bending moment diagram, we can utilize the area under the shear force diagram. So to begin, we have a rectangular area of negative 20 times 15 that is equals to negative 300 kilopound fit. Since the slope is 0 for that region in the shear force diagram, on the moment diagram it will be linear. Next, I have a triangular zone and we can calculate the area of the triangular zone by half base into altitude that is coming around 450. So our moment diagram will jump up by adding 450 to negative 300. We get a value of 450. Next, we have to figure out the profile. Since we have a linear profile in the shear force diagram and integrating that, we will get a quadratic profile for the moment diagram. Similarly, calculating the area of the triangular zone next to it, it is coming negative 450. So our moment diagram will jump down from 150 to negative 300. The profile again will be quadratic since we have a linear profile on the shear force diagram. Finally, we have a rectangular area in the positive zone that is of 300. So our moment diagram will jump up to 0 and the profile will be linear as the slope of shear force diagram is equals to 0. In order to figure out the shear force and bending moment diagram, we first need to figure out the support reactions at point A and B. Since all the loads are acting vertically downwards, we are interested in the vertical support reactions. So writing our equilibrium equation of summation of forces acting along the y-axis equals to 0, we can simplify the expression as AY plus BY equals to 1200. Next, the second equilibrium equation can be written as summation of moment at point B equals to 0, taking counterclockwise as positive. Our resultant value of AY is coming 450. Now plugging in the value of AY into equation 1, we can get the BY of 750 pounds. Now once we have the support reactions, we can now draw the shear force and bending moment diagram. So to draw the shear force diagram, we recall that point loads basically cause either jump up or jump down on the shear force diagram. So since at point A we have a load of 450 going upward, so our diagram will jump upward at 450 pounds. Next, the load is of 200 pounds that is acting in the downward direction. That will cause the jump down from 450 to 250. Similarly, there is a jump down of 400 at 12 feet from point A, and again a jump down of 400 pounds that is at 18 feet from point A. That will cause our shear force diagram to go to negative 550. Finally, at point B, there is a force of 750 going in the upward direction and 200 pounds going in the downward direction. The resultant force is 550 pounds going in the upward direction. Next, we can draw the bending moment diagram utilizing the area under the curves of shear force diagram. So, starting at point A, since there is no area at point A, so we will start the bending moment diagram as 0 pound fit. Next, we have this rectangular area of 450 times 6. If we multiply them together, we get 2700. That will be the bending moment at the location where 200 pound load is being applied. Next, we have to figure out how this moment is changing from 0 to 2700, and we figure that thing out based on the slopes. So since the shear force diagram has a slope of 0 at this point, for the bending moment, the slope will be linear. Next, we have an area of 250 times 6. If we multiply them together and add up the 2700 in it, we get 4200. Similarly, we have now an area in the negative zone of 150 times 6. So we have to subtract from 4200 the 120 times 6, and it gives us 3300. Finally, in the last section, we have to subtract again 550 times 6 from 3300, and it gives us the value of 0. In order to find the centroid of a composite body having known shapes, we just need to identify the centroid of each one of those shapes and multiply with its area, and then divide it with the total area of the body. Here, since the object is symmetrical about the y-axis, so we are mainly interested in the location of centroid along the y-axis. So to start, we have a semicircle having a radii of 300 mm. We can calculate the area of it by pi r square and then divide it by 2 for the semicircle. It is coming 141.3 10 raised to power 3 mm square. Next, the centroid of a semicircle lies along the vertical axis at a distance of 4 times radius divided by 3 pi from the base of the semicircle, which is coming 127.3 millimeter. Next, I have two right-angled triangles. I can calculate the area using the formula half times base times altitude of the right-angled triangle. In this case, the base is 150 millimeter and altitude is 600 millimeter. Since we have two of those right-angled triangles, the total area is coming along 90 10 raised to power 3 millimeter square. Next, the centroid of the right-angled triangle is 1/3 from the higher end of the triangle. Since I have a base of 600 millimeter, 1/3 of 600 is equals to 200 millimeter. Next, we have a rectangular object here having the dimensions of 300 millimeter by 600 millimeter. The area is coming at 180 10 raised to power 3 millimeter square, while the centroid of it lies at a distance of 300 millimeter from the origin. Finally, I have a hole that is present in the middle. In this case, this area needs to be subtracted. So we will calculate the area of this smaller circle that is coming 31.4 10 raised to power 3, and its centroid lies at the origin. Next, we can go ahead and tabulate all of this information and figure out the product between the centroid and area of all the individual shapes, taking the sum of it and dividing it with the total area of the composite body give us the value of centroid, which is coming 142 millimeter in this case. In order to find the moment of inertia about an axis parallel to the centroidal axis of an object, we can utilize the parallel axis theorem. That is, summation of moment of inertia about the centroidal axis and the product between the area of an object times the square of perpendicular distance between the centroidal axis and the axis along which we are calculating the moment. Here we are given a composite shape that is made out of 3 rectangles, so we can calculate the moment of inertia for each one of them and then add them up together to calculate our total moment of inertia about the y-axis. So to start, segment 1 has the dimensions of 1 inch by 8 inch. So let's first calculate the moment of inertia about its centroidal axis. The formula for that is 1/12 bh². Here the value of b will be 8 inches since that dimension is parallel to the y-axis across which we are calculating the moment of inertia. Plugging the values in the formula give us the number 0.667 inch raised to power 4. Next, we have to project this thing along the y-axis. So utilizing our parallel axis theorem, we have to identify the distance between the centroid of the rectangle to the y-axis. In this case, the value is coming 9.5 inches. So plugging it in our formula, we are getting a value of 722.67 inch raised to power 4. That is the moment of inertia of segment 1 about the y-axis. Now let's look at our segment 2. Here, the dimensions of the segment 2 is 8 by 1 inches. Now, again, first thing we have to do is calculate the moment of inertia about the centroidal axis of this segment. Here, the value of base will be 1 inches as it is parallel to the y-axis, whereas 8 inches is the dimension that is perpendicular to the y-axis, that will be the height of the rectangle. The value of the moment of inertia about the centroidal axis is coming 42.66 inch raised to power 4. Next, we have to figure out the distance between the centroid of this individual rectangle to the y-axis, that is coming 5 inches. Plugging those values in the formula, we get the value of moment of inertia of this rectangle about the y-axis equals to 242.67 inch raised to power 4. Finally, we have our segment 3 having the dimensions of 3 inches by 1 inches. Calculating the moment of inertia of this rectangle about the centroidal axis gave us the value of 0.25. Now, the distance between the centroid of this rectangle to the y-axis is 0.5 inches. So, taking the square of that 0.5 and multiplying with the area and adding up that with our moment of inertia about the centroidal axis give us its value about our y-axis. Now, once we have all the individual moment of inertia of 3 segments, we can add them up together to calculate the total value, that is coming 966.34 inch raised to power 4.